Hello everyone, it's me again, Dave. It's been 3 years since I last uploaded my very first video in this channel. It was about Gaussian integral. I was still high school then, and then now we're back. I'm basically college now. I've been pretty busy with school, but lately I've been finishing up my SEM, and basically I have nothing else to do now. Okay, so yeah, I've decided to basically revive this channel since I find it very enjoyable to just share random stuff that would probably be helpful to whoever stumbles upon this video. So basically, yeah. Okay, so just to start things back, let's try to answer a very interesting integral. It's very interesting because the process is pretty simple, but yet it's so elegant. Okay, so let's first do inspection with our integral. Let's try to inspect that muna. So we have ln of sine x dx uh, evaluated from 0 to pi over 2. That's the integral. Via inspection, you can immediately tell that it doesn't have an elementary antiderivative because you have an inner function, yet you don't have a du outside of this inner function. So it's a bit tricky to evaluate because you can see that it doesn't have an elementary antiderivative. But lucky us, this one is a definite integral. So, and then we know that there are techniques in evaluating uh, definite integrals even if it doesn't have an elementary antiderivative. Okay. Um, so, okay, I can enumerate techniques. So one way is the Feynman technique. So you basically introduce another variable into your system and then manipulate from there to extract a value of your definite integral. Or another thing that you could do, so that's basically what we did in our very first video in the Gaussian integral. So we introduced a variable y, and then yeah, we did some double integration. Other thing is you could multiply something. You could multiply something to your integral that is symmetric to it. Symmetric. So basically, you have f of x, g of x. So you if that multiplication is beneficial in you getting the evaluation of this integral, then yeah, that could be a technique. Another thing is that you could do addition. Let's say alpha I. So you basically add a function g of x that is linearly related to your original integral. Okay. So another useful technique in evaluating these types of integral is abusing the linearity property of the integral. Okay, so for example, suppose you have a say AB. Suppose you have an integral of f of x dx. Okay, it's equal to this one, and then it doesn't have an elementary antiderivative. So and that, but then via manipulation, you get this expression, something like maybe alpha uh, a to b of f of x dx, and then you get a constant. Let's say a constant, something like uh, constant c. Sorry, let's move it a bit. C dx a to b. What you could do here is you basically transpose this one because the integral operator is linear. So you basically get 1 minus alpha integral of a b f of x dx. Since this is a constant, you can just evaluate that into b minus a, basically. And then, for you to get the original value of your integral that doesn't have an elementary antiderivative, you just divide this by 1 minus alpha. So, without having to know the elementary antiderivative of your f of x, you can still evaluate it via manipulation. Okay? So, the technique here is you have to induce a constant in your equation. You have to somehow introduce a constant that you can use to evaluate the function. Okay, so uh, let's inspect again. let's look at what's inside our ln. Inside our ln is sine 2x, basically sine x. Okay, so what trigonometry identity can I use such that I can induce a what do you call this? A constant in the right hand side of my equation. Okay, the first thing I can think of is that I can make use of uh, sine x cos x is equal to sine 2x all over 2. This is the double angle identity. Okay, so if I can introduce a cos x here, basically I'll get, okay, so ln of sine x cos x, and then I'll get ln of sine 2x, sine 2x minus ln of 2, because it's over 2. So you can uh, you can subtract minus ln 2 instead. So basically, on your right hand side, you now have a function that is linearly related to your what do you call this? Linearly related to your function, and then you have a constant. Then that's a very good start. So what do we introduce in this system? So we basically um, we have to add a function. We have to add, because this is ln of sine x, this is the original function. We have to add ln of cos x. So if we want to add, we first have to investigate what's the relationship between ln of cos x and then ln of sine x. Okay, in this context, of course. Okay. Okay. So my initial guess, what's the relationship between the integral of 0 to pi over 2 of ln sine x and then the ln of cos x? My initial guess is that they are equal, because why? What's my basis for that? So my guess is ln, the integral of 0 to pi over 2 of ln of sine x is equal to the integral of 0 to pi over 2 of ln of cos x. Alright? Sorry for the dx. So what's my basis for this? First, you have to look into the graphs of sine x and cosine x. Okay. So suppose we have here, let's say cosine. So basically, it's periodic up until 2 pi. That's cosine, and then this is pi over 2. And then the sine one, it starts at 0. It starts at 0, and then, okay, sorry, it's so ugly. And then it's periodic up until 2 pi. Okay, now let's investigate this part, 0 to 2 pi, because that's the only part wherein we're interested. Okay, it's ugly. Okay, let's draw it separately then. Like this. Okay, let's only draw the 0 to pi over 2 of sine. Okay, that's the only part where we're interested. So pi over 2. Okay, so if you can see, it's just a mirror. This one is just a mirror of this one. So if we put this in ln, if we into if we do an ln operator from this whole signal, you basically get a symmetric, basically just an inverse, not an inverse, but like inverse in the time aspect. Okay, so basically a time inverse. Okay, so my guess is that they're equal. So it's pretty obvious here. But then, just to be formal, let's prove that they're equal. Okay. So we start here, ln of sine x. Okay. So we have 0 to pi over 2. Okay. So what is ln of cos x in terms? What is ln of sine x in terms of cos x? So basically, ln of sine x in terms of cos x is ln of cos x minus, sorry, ln of cos x minus pi over 2, then dx. Alright? From here, we can let u be equal to what's inside, so x minus pi over 2. And then du is 1 dx. And then our bounds will become, so bounds 0, it will become 0 minus pi over 2. It will become negative pi over 2. Okay? And then the other one is, so negative pi over 2, and then the other one is 0. Okay. Excuse me. One moment. And, oh, sorry. A minor mistake. Lol. ln of sine x is basically pi over 2 minus x. The opposite. So it's negative. You have to remember that. Dx. And then, okay. So we let u here. Let u is equal to basically what's inside this one, so pi over 2 minus x, and then du is equal to negative 1 dx. So our bounds will become, so 0, pi over 2 minus 0 is basically pi over 2, and then pi over 2 minus pi over 2 will become 0, so pi over 2 to 0. Okay, so we basically get pi over 2 to 0 of ln of, negative of ln cosine u du. Now, since it's negative, we can just flip our bounds. So we can just flip our bounds and then remove the negative one. So we get pi over 2, 0, and then ln of cosine u du. Hence, we started here. We started at ln of sine x. We started here, ln of sine x. We ended up at ln of cosine u. So basically, we can conclude that this is also equal to 0 to pi over 2 ln of sine u du. Okay, so we've proven that indeed the integral of 0 to pi over 2 of ln of sine x dx is equal to the integral of 0 to pi over 2 ln cosine dx. Okay, that's a good one. Okay, so we have this property now. Okay, we can set this aside. Setting that aside. Okay, so this is our function. Okay, diba we wanted to introduce a cosine x. So how do we do that? We do that by since we know that this is equal, so this is, if we 0 to pi over 2 of ln of sine x dx. If we add this one, if we add this function here, 0 to pi over 2 ln of cosine x dx. So since we know that they're equal, so we just put 2i here. So it's equal to 2i. Alright? And then via the property of natural logarithms, we can just do 0 to pi over 2 of ln of, so combining the two, so you get sine x cos x and then dx. Okay, so basically we get 2i, and then we using the double angle identity, so you get 0 to pi over 2, and then this is equal to ln of sine 2x all over 2 or minus ln of 2 dx. Okay, so just to see things, we separate this one. So 0 to pi over 2 ln of sine 2x minus dx minus the integral of 0 to pi over 2 of ln 2 dx. Now this one we can evaluate. Okay, so 2I is equal to 0 to pi over 2 ln of sine 2x dx. Okay, let's evaluate this one. So we basically have minus ln of 2 pi over 2. Okay, nice. And then what you could do is we transpose it, so you get no. Okay, for now let's transpose it. So 2I plus ln of 2 plus pi over 2 ln of 2. Okay, and then it's equal to this one, 0 to pi over 2, and then ln of sine 2x dx. Okay, and then we have to evaluate this one. I have to evaluate that. Okay, we can let u is equal to how do we evaluate this? Okay, we let u is equal to 2x, and then we get a du of 2 dx. Alright, and then we get a bounds. So the bounds is basically 2x, so it's just 0 to pi. Yep, 0 to pi. Okay, so where are we? There we go. 2I plus pi over 2 ln of 2 is equal to, so our bounds is 0 to pi, and then we have ln of sine u du. Now what's this? Basically this is basically 2I, because our given was from 0 to pi over 2, right? Our given was from the integral of, okay, what was I? I was 0 to pi over 2 ln of sine u. Tama. So it's for 0 to pi over 2. We know sine is symmetric. By the same reasoning, we can just say that this whole thing is basically 2I. Okay? So since this is 2I, okay, no, wait, 2I nga ba? Ln sine of u, wait, ln sine of u du, and then it's from 0 to pi. Oh, my bad. Okay, there we go. This is the wrong part. Dx, so we have to divide by, kasi yung du natin is 2dx, therefore dapat 1/2 ln sine u du. Okay, so this is basically okay, so 1/2. Tama. Okay, so basically we have 1/2, and then this is basically equal to 2I via same reasoning of symmetry kanina, kasi our I is from 0 to pi over 2 ln sine of u, and then we know that sine is just symmetric around pi over 2. It's symmetric, the area is symmetric. Therefore we can conclude that this whole thing is basically 2I. Alright, so if that's 2I, you can simplify things. 2I plus pi over 2 ln 2, and then we get 2I minus 2I minus I is equal to minus pi over 2 ln 2. Then finally we get I is equal to negative pi over 2 ln of 2. So this is our final answer. Now, you see, you didn't really have to take the have to get the elementary antiderivative to evaluate a definite integral. You can just abuse properties via linearity property. You can just add, multiply functions as long as it's gonna help you induce a constant you can use in order to evaluate the original integral. So yeah, it's a pretty neat integral since we started here. We basically started here. Like we seem so lost here because we know that this one doesn't have an elementary antiderivative, yung ln of sine of x. But then we have some techniques. We have some techniques in doing that because we know that this one sine x and cos x is basically equal. We've proven that, and then via double angle identity, we were able to induce a constant minus ln 2 dx. Okay, so from that, it was just trivial. We just uh, what do you call this one? We just evaluated the constant and then express this term in terms of I, and then we basically ended up with an I is basically equal to minus pi over 2 ln 2. So the takeaway here is that um, um, even if it seems like it doesn't have an elementary antiderivative, what you can do, you can have a starting point. You can do inspection and then see if you can introduce some function of symmetric nature to your integral that will help you in evaluating it. So basically just play around the integral in your mind and think of functions. Okay, you can think, if I multiply this with a symmetric function, will it help me in my integral? So as you can see, it's very similar to the Gaussian integral. What we did in the Gaussian integral is that we multiplied it by what do you call this one? A symmetric function, but in a different variable, and then we basically evaluated it in 3D. Okay, so yeah, it's very similar to that. So I, yeah, I guess that's it. I'm sorry if the video is very raw. I just wanted to share my thought process in doing integrals like this. I find it really beautiful because you don't really have to know the elementary antiderivative. You can just manipulate. You just use algebra basically in order to get a value out of it. So yeah, I hope you got some takeaways out of this very interesting integral. And then I hope to do a lot more videos in the future featuring very interesting integrals. Pretty okay, very similar nature yung siguro yung next videos ko. Mga integrals, mga similar pa din yung techniques. Mag-introduce ka. Magma-manipulate ka lang ng ng integral. Basically algebra lang. And then you get a value out of it. So yeah, I hope you enjoyed this video. See you in the next video. Bye.